Welcome back. In this lecture, we'll begin exploring the different ways we can generate random variables in NumPy. We'll start by defining what a random bit generator is and how it operates. Let's begin with some code first, and then we'll explain what it does. We start by importing two things from NumPy's random module, generator and PCG64. We do so by typing from numpy.random import generator as gen. And on the next line, we write from numpy.random import PCG64 as PCG. This enables us to use the generator function as well as the bit generator PCG without having to write np.random or their full names every time. All right. So the generator function takes a bit generator as input and creates generator objects as outputs. As a matter of fact, these objects are instances of the NumPy's generator class. So we can use the various methods of the built-in class to create arrays of random data. Then there's the bit generator PCG64. The abbreviation is short for permutation congruential generator, and the function itself is a 128-bit implementation of O'Neill's PCG. We don't need to get too technical now, but the latter contains function pointers that can produce decimal or integer values of up to 64 bits in size, hence the name. The best way to understand these functions is to get our hands dirty with some coding. We'll start by defining array RG and setting it equal to gen before adding PCG in the parentheses. Of course, RG here is just short for random generator because we want a suitable name for the variable. Then on the next line, we'll call the normal method on our newly defined NumPy generator variable. The output is a single numeric value, which was generated from a normal distribution. In fact, it was generated from a standard normal distribution based on the default values for the location and scale arguments. If you need a reminder, we can get a quick look at the documentation by holding Shift and pressing Tab when we have our cursor on the method. We can also specify the size argument of the method to indicate how many random values we want to be generated. If we input a single scalar, the output will be a one-dimensional ND array containing that many randomized values. Similarly, if we input a tuple as the size, the output will be an ND array with the same shape as the tuple. Superb! We've discovered how to create a random variable, but the values on our screen probably differ from the values you see on yours. That's because every time we call a method, the generator randomly selects what is known as a seed. A seed is a set of starting parameters for the algorithm which generates the random values. Thus, every time we run the cell, we'll get different values. This is fantastic if we always want to produce different results, but it makes it rather difficult to use in practice. For example, if we're trying to create a random dataset to test a model, we won't be able to extract any meaningful insight because we'd be plugging in different values every time. To avoid this, we can use PCG to specify a seed for the generator object. This will ensure that every time we run a given function with the same arguments, it will give us the same output. To see this in action, let's redefine array RG, but this time also pass a value to the seed argument of PCG. The seed needs to be a numeric value or a sequence of numbers. So, since we're the 365 team, we'll just use 365. Of course, you're free to use anything you like, but using 365 will ensure your outputs match ours. On a new line, we also want to call the normal method once again and compare the results. We see another 5x5 matrix, which is completely different from the one we had before. Even if some of the elements in one matrix look similar to their corresponding positions in the other one, this is solely because both are products of the same method with the same starting parameters. However, if we rerun the cell where we specified the seed, the output stays the same. Hence, for this specific seed, the 5x5 matrix below is the result we expect to see every time we generate an array of normally distributed values. The next bit is extra important, so please pay close attention. However, if we call the normal method in a new cell and rerun it, that'll result in a different outcome. In fact, we can run this cell several times and we'll see that each one returns a different array. The reason is that a seed only lasts for one execution of a method or function before it is reset. And this feature serves to prevent unintentionally setting the seed once and forgetting to reset it later. Doing so might result in multiple identical datasets, which we usually want to avoid. Hence, whenever we intend to use a seed, we'll have to reset it every time. Fantastic! Now that we know how to generate random values from a normal distribution, we're ready to examine other useful methods of the generator class. In the next lecture, we'll learn how to get integers, probabilities, choices, and more. Thanks for watching.